Okay, so we are back for more on energy. So in today's video, we are going to be continuing our study into work and energy, and we're going to be doing another video a little bit later that works with Hooke's Law Lab that we did last time in class. Okay, so this is where we were going to go in class last time, but we needed to do a little bit more review, and we ended up doing a lab. So here we go. We have two friends who are cycling up a hill. That hill is at 8 degrees incline. That's really steep for bicycle riding. So the stronger cyclist is going to help his friend up that hill. So if you can imagine it, you've got a hill at 8 degrees, you have people on their bicycles, and so one friend is going to give the other one a force. That force is 50 newtons. It's pushing up the hill, and it is parallel to the hill. Now, this is key. So if we can imagine that bicycle rider that's getting the push as a point mass or a box, he's getting a push that is parallel to the hill. That's a 50 Newton force. Now, he is going to move a distance of 100 meters up the hill. So if he moves from here to here, and that linear distance along the hillside is 100 meters, if we need to find the work is force dotted with distance. Now, I'm going to keep saying that because it is a vector product, specifically a scalar product. We have two vectors. We are going to multiply them together in a very special way. Basically, work is the force parallel to the motion times the displacement that we travel along that motion. In this case, that 50 newtons is parallel to the path that the person is traveling. And that displacement is 100 meters. So what we get is that that person has done 5,000 joules of work. 5,000 joules of work just helping his friend up the hill. So, couple of things, let's just get this cleared up and out of the way. It is super tempting to equate the work done on a system with the force that's exerted on it. The thing is that we can exert a low force but take it a farther distance. That's the basic principle behind many of our kind of simple machines. I may not be able to lift a really huge box, but if I put it on an incline, I can move it up that incline and eventually get it to the height that I need it, whereas I can't just deadlift it straight up there. So sometimes we have to work a little bit smarter, a little bit harder, but we'll get it there in the end. So we go a longer distance in order to do a lower force. Same amount of energy happens, but so be it. So in physics, there must be a displacement. You've heard me say this. If you go no distance, you do no work. That is kind of that thing. You must go the distance. Force and work are not equivalent. They are not the same thing. Okay? So force is a vector, work is a scalar. So what happens when we do work? Work that is done on a system, again, on a system, so that means we're dealing with positive work by an external force, means that we are changing the energy. If you think of the energy of a system kind of like a bank vault or like a piggy bank, we are putting a deposit into the system. So we are going to either increase maybe the kinetic energy, maybe the object is going to have a greater velocity. We could be changing the gravitational potential energy, the elastic potential energy, or maybe even the internal energy of the system. We are changing something. So remember, energy can neither be created nor destroyed. It just changes form. So the question we have here is, do you think that the transfer of energy can happen if the work is zero? Give it some thought. Puzzle it out. That's going to pop up in class again. So as we look at the total energy of the system, the total energy, big E, of our system is the kinetics. This is our energy of motion. Our gravitational potential energy, or GPE. Our elastic potential energy, or our EP. And our internal energy. So we take everything and we add it all the way up. So if no work is done on the system, will the total energy change? That is the question. Will the system energy change? So when we look at that, we need to remember we're looking at what we would consider to be an isolated system. So we can neglect interactions with its environment. So external objects do zero work on the system. The system can be considered isolated. Oftentimes, when I draw these in class, or even when we draw these here, you'll notice that we have kind of like this dash lines that we say, okay, this is our system. This is our glass bubble, if you will, so that we can isolate what's happening. So let's look at some examples here. So here is a video that we're going to look about a system. Okay, so what did we notice? Well, we noticed that he wasn't always starting the car from the highest point on the track. So even though the incline of the track would change, we weren't starting at the highest point every single time. What you may have noticed with that ruler there, and yes, we're on a video, you can go back and watch, is that they were trying to keep the height of release the same. So they were looking at a frictionless track. The bottom of the track is near the edge of the table. The track was tilted at different angles. So the car and the earth is the system. Okay, so the car and its interaction with the earth. That, see the red lines right here? And right here. That's the system, the car and the earth. Everything else is outside of that. So if you'll notice, that metal can that they had never got moved. And they hit it every single time. In order for that to happen, at the edge of the table, that velocity had to be the same every single time. Now, how do they do that? The car starts at rest. So up here, the velocity is 0. Down here, the velocity is some v. Well, here, my velocity is 0. And down here, in order for it to hit the exact same spot, we have to be going a constant velocity of v. So what you notice is they released at the same height. They start with the same gravitational potential energy, regardless of the incline of the ramp. They start with the same height. So they start with the same gravitational potential energy that is then transferred into kinetic energy. And that is the piece that creates this velocity being the same. So Is the energy of an isolated system constant? Yes. When we released the cars from the same vertical height, they landed the same distance from the table. They both hit the bucket. So as long as, if we are doing work, let's go back to our equation for a second. If we are not having any work come in, what we just showed was that these two can change as long as their sum stays the same. Well, in reality, any of these could change as long as their sum stays the same in an isolated system. If we are not doing work, we're not adding energy into the system, we're not taking energy out of the system, we are just transforming it from one to another. It's like having money in the bank, and maybe some of it is in your checking account and some of it is in your savings account, and maybe you transfer some here some weeks, maybe you transfer some back other weeks, but the total amount stays the same. That is what we're looking at. Okay, so let's look at work energy bar charts. A work energy bar chart is going to indicate the relative amount of a system's type of energy in different processes in that state. So it allows us to basically have a visual of where our energy is. So the work bar chart will be shaded slightly differently, and that emphasizes that the work is not initially in the system, that it's coming in. So if we push a ball of clay along a frictionless table that's exerting a constant force, initially the ball is at rest. That means our kinetic energy is right here at 0. So we do work, we put a force on that ball, we push it across the table, so we are bringing work into the system. So you'll notice that this box right here is shaded. That's saying, hey, this wasn't in the system already, we brought it in. And so after we put those two together, what we have is we have that the ball is moving, and we have a final kinetic energy. So you can see that a flat line plus this nice little pretty shaded box is going to give us this shaded box. So now at the edge of that table, a ball going at some velocity v then falls. So what's happening? Well, at the edge of that table, it has kinetic energy. Now, based on its position to the Earth, it has gravitational potential energy. So those are both part of the system. There are no external forces to the ball Earth system doing work, so you'll notice that this is a nice flat line here. Nothing else is happening. So what is happening is as the ball goes down, you may realize that the magnitude of the velocity is increasing. As we get to the ground, the gravitational potential energy goes to 0, and all of that energy is transformed into kinetic energy. So what you get is that the initial kinetic plus the initial potential, which is gravity, in this situation is going to equal just the final kinetic energy, because the other terms are 0. Now, is this a formula you're going to have to memorize? No. Is this kind of a situation you're going to need to sketch up, look at? Yes. So this is like forces. You're going to need to analyze, draw a picture, set it up. So here we have the clay ball is going to land on the floor and just stop. What happens? Well, where does the energy go? Well, there's work that is done on by the floor, on the ball, right? creates the stoppage. So that energy is now part of the internal system of the ball. What happens? Well, the ball had to stop. That shape, you'll notice that it's no longer a perfect circle. That ball of clay is now squished. Shape changes. That's a change in the internal energy of the ball. So we're going to come back to this in just a few minutes.